Hi everyone. This is the lecture that I had scheduled for September 9th. This is on section 1.5 in our textbook. We're going to go over a theory-based approach for this section. And you might find that the theory-based approach is ultimately easier to do than with the simulations. Certainly you don't need the app to do the theory-based approach. But there are some restrictions on using it. So let's go forward and see what we can do with this. Okay, so um, the biggest difference between the two of either the theory-based or the simulation-based method is that the theory-based, we basically can use just the hypothesis that we make, and we'll get uh, values out of it, actually the standardized statistic, which would be a little faster than when we go through the actual app. Okay, so in all the things that we've done before, remember we've made the null distributions, and the shape of those curves tend to be the same. And in fact, we can predict this shape using what's called a normal distribution. Now, normal in this sense, is a technical term. A normal distribution, like the normalized statistic, has to do with more like the word averaged. It does not mean ordinary. There are other distributions, like the Poisson distribution and a geometric distribution, things of that sort, which we really won't get to in this class. But while you see normal used in this context, think of it as a technical term, not a synonym to the word ordinary. Okay, so we'll see how our p-values differ between what we do between a simulation and what a theory-based approach will take. So what we had before was our null distributions, the things that we simulated that weren't based on our testing so much as what the hypothesis was predicting. It was this bell-shaped curve, and then it's centered under the proportion that we hypothesized for the null. So if our null hypothesis is 0.5, uh, uh, we would expect the middle of this to be under that value. And you can see from the scale on this, if you look at about where 0.5 is, that's about where it peaks. Now the width of this null distribution, as we saw before, would vary by the sample size. We would get a narrower null distribution for a large sample, wider distribution for a smaller sample. Okay, so if we compared null distributions, the one on the left is a null distribution for a sample size of 30, and the other side, the one that's more dense, is a sample size of 300. And actually both of these, even though they're quite different, we can predict using normal distributions. So let's see what it takes to be able to use a normal distribution from a theoretical standpoint. Okay, so here I have 6 graphs that were taken from earlier examples. I don't think we did yeah, I guess we did all of them. The component faces, the rock, paper, scissors, the Doris and Buzz, and the hospital heart transplant simulations. You can see that the component face method, that's pretty tight. There you have a high density of numbers, so that n equals 279, and your parameter is 0.5. That looks nice and normal shaped. The same with the second one over, the n equals 32. You see it's a little bit sparser in data, but still the same shape. And also with the St. George's, n equals 361. And notice that the shape stays the same, even though the parameter, the pi, is 0.15. So we did hypothesize a lower value, but nevertheless, we do get the same kind of distribution. So the top three, you can see they're all very similar in shape. On the second row, you have the rock, paper, scissors, where n equals 12. And you can see something happens that makes it not quite distributed. The parameter is 0.3. That seems to be about the peak. But notice that on the left side, it's a little bit more constrained because you can't go below 0. And on the right side, it tails off a little bit more slowly. So this one doesn't have that symmetry that we're looking for. And the middle one, with Doris and Buzz, we only have 16 samples, and the distribution is 0.5, but we do have, a nice symmetric shaped curve, and so perhaps this one, normal distribution from a theoretical standpoint, is warranted. The third one, you can see where we have St. George's. This is with the 10. Remember, there were 10 cases that we looked at, and we were hypothesizing the mortality rate was 15%. And you can see that this one is just like the rock, paper, scissors one, where it's a little bit skewed, where we don't go down to 0. It kind of ends abruptly on the right side. So what do we have in common between the ones on the bottom that make it different than the ones on the top? Well, other than the middle one, the Doris and Buzz one, what we have are just a small sample size. And that turns out to be one of the key things that will allow us to use the normal distribution theoretical method instead of having to make simulations. Okay, so the shape is affected by the sample size and the proportion we're testing. Larger sample sizes are better. The closer we are to a proportion of 0.5 is better. Remember the one that was in the lower middle, that even though the sample size was pretty low, it was still symmetrical. So we can actually come up with a rule that will allow us to use the theory-based method. So you should have at least 10 successes and 10 failures in the sample to be confident that the normal distribution will fit the simulated distribution nicely. So what that means is that when we were looking at that result of the heart transplants where we had 10 samples, well, we only had 8 successes and 2 failures. So clearly we fell short on both of them. So the thing to remember is that it's not just how many successes you have, but it's also how many failures. So if you have a minimum of 10 successes and 10 failures, you have at least a sample size of 20. But it's still possible if you have a sample size of, let's say, 50, and you have 45 successes and 5 failures, that wouldn't be a valid condition either. Okay, so the advantages that we'll have with this theory-based set is that we don't need to set up a randomized method. It's fast and it's easy. It can be done with a wide variety of software. In fact, you usually do it with just your calculator. And we'll get a good p-value, very close to what we get on the theory-based. And every time we do it, we'll always get the same p-value. And we'll be able to do something called confidence intervals, which we'll talk about in a few weeks. The disadvantages is that we have the validity conditions. We need to make sure that our number of successes and failures for a single population will be at least 10 each. Okay, so let's go through an example. And this is a fairly simple example, so we should be able to see some results without spending too much time on the details of this. So here's a researcher looking at whether children show a preference for toys or candy when they go trick-or-treating. And so they tested 5 Connecticut neighborhoods, and they offered them 2 plates, one with candy, one with a small toy. And so the researchers ultimately observed the selections of 283 trick-or-treaters between 3 and 14. Okay, so we look at this and we know the null hypothesis here is 0.5. And the null hypothesis is 0.5 because we don't know. We haven't hypothesized whether they would choose candy or toys. And all things being equal, 0.5 would be the best initial guess that you would make because you wouldn't have any basis for hypothesizing anything different than 0.5. So the alternative is that it's not 5. Now, remember what we said about single tail and double tail. We don't know if it's going to be higher or lower, so we want to test to see is it different than 0.5, not just is it greater than 0.5 or less than 0.5. So our alternative hypothesis is pi doesn't equal 0.5. And so notice we're focusing on the candy here, but we could have easily focused on the toy, right? There's no real driving motivation to have one or the other. Okay, so let's look at the results then. The results were that 283 children, 148 of them chose candy and 135 chose toys. Okay, so that's not 50%, it's something different. So let's use the applet and just the way we did using the simulation and see what we have and see what we got with the null distribution and the standard deviation. So I fired up the applet, and this is what I got. Okay, so the probability of heads was 0.5. Well, the probability of choosing candy was 0.5. The number of observed cases or tosses was 283, and I did this 1,000 times. And I'm doing this with the number of children who chose candy. I could have done proportion as well. And you can see on the chart, here I click summary stats. Here we have this nice bell-shaped curve, so that's indicative that that 283 was a pretty substantial sample. The mean was 141, which you would expect, which is right in the middle of 283. The standard deviation is 8.3. Now, you can see that the red areas are the cases of our simulation that turned out to be more extreme than either 148 or above, or if we look at the other side, it would be 135 and below. So that both of those are the same distance from the 50% of 283. And you can see we get a p-value here of 0.47. Now that's a very large p-value, and so we really don't have much support that says that children in general would prefer one over the other. We'll come back to this with a little addition on there in just a moment. Okay, so could we have predicted the center and the shape of the null distribution? Well, with the number of samples we had, we could. And the standard deviation? Well, the standard deviation we can calculate, and we'll have ways to calculate that as the course goes on, but the formula that we would use for the standard deviation in this case is that we would take the square root of the parameter pi times 1 minus pi over n, where n is the number of samples you have and pi is the proportion. So if we stick in the values that we had, 0.5 times 1 minus 0.5 over 283, we get a standard deviation of 0.0297. Okay, so we make a note of that. And so we see that we have 148 successes and 135 failures. So we can use the theory-based method. And the theory-based method, we use a normal distribution chart, but our applet will also calculate normal distributions. So for now, this will illustrate what we're doing just from a theory-based. And so here, what I've done is I've added, you see on the bottom it says, of course the options was I was going to do two-sided, and the normal approximation. I noticed some of you, when you were doing your one applet or your one proportion applets in group work, that you click that box that says normal approximation. And you can hardly see it on this, but you can see just at the very top, you see there's this gray area. And so the gray would be the shape of the normal distribution. It wouldn't have the jagged edges of our simulation, but it would follow that general shape. And you can see the p-value that we get is 0.4397. Compare that to the simulated p-value of 0.47. So we have the same conclusion here as we did before, but what's different here is the fact that we didn't have to run the simulation. We could have done this with a normal approximation. Now the z-value, the z-score is 0.77, which is not enough information to reject the null hypothesis. Now notice also that I have the standard deviation of 8.3, and we calculated a standard deviation with the theory-based method as something different. That was 0.02. And what that is that's a normalized value. So we'll still be able to use both of them somewhat interchangeably, but when we have that bottom scale of the number of heads, you can see what those numbers are. If you switch that, and I suggest you do this, try this with the app, choose the statistic of proportion of heads. So you'll, instead of 148, you'll put in 148 divided by 283, and then you'll see that we get a standard deviation that's nearly identical, because the x-axis won't be from 99 to 171, it'll be from 0 to 1. Okay, so the p-value is very, very similar to what we got from a simulated, and it's not small, so we really don't have any evidence that says we can reject the null hypothesis. Is to look at, what I'd like you to do is to look at this particular thing where we went back to the rock, paper, and scissors test with 12 repetitions. One of the repetitions had scissors thrown down. What I'd like you to do is do the one proportion applet to test the hypothesis, that it'd be 1/3, but then also look at the normal approximation results. And so what you're going to see is the difference between the theoretical and the simulation based, and you can see that we don't have enough successes or failures. We had 1 success and 11 failures with the condition that I'm giving you. But it would be a good practice for you to do that anyway. So at this point, I'll leave it, and we'll discuss this more and do a little bit of classwork on Friday to continue this topic. Okay, the standardized statistic is 0.77, and if you go back to those numbers I gave you earlier, that's certainly not any support to reject the null hypothesis. Remember, we had to be 2 or more to draw the conclusion that the null hypothesis is perhaps wrong, and we don't even have 1. So so clearly in this test, we don't see that that there's any support, but you can see the calculations we went through, we got pretty much the same thing. So what I'd like you to do after this now